Yes, so the problem with linear algebra is that if you put it on the line with support for scalable kernel methods, you get 2 lines, and the line break didn't look very good, so hence it's abbreviated. But that really is the perspective that I'm coming from. Not the perspective that all of my collaborators are coming from, so there's a bunch of people who are involved in this. The stuff that I'm talking about today is stuff that I've been directly involved in, and therefore feel some responsibility towards. But the last couple of people on this slide, so Jeff, Killian, Andrew, and Jake have been putting the stuff that I've been talking about and other stuff that they've been working on into a software package called GPyTorch, which is GPU accelerated. It has some nice linear algebra support, so I will advertise that too, and I think I have a pointer at the end. But anyhow, so I don't have a prayer, I think, of being quite as active as Paul was yesterday, but I can at least start with a good teaser question. So suppose that you've got 2 variables, u1 and u2. I've drawn them in the plane, but they don't have to be scalars. I give you u1, what's u2, right? And of course the question is pretty much meaningless at this point. You need an assumption in order to say anything. So we need something that's going to relate u1 and u2. And I would claim that there's 2 basic ways that we think about this when we're doing kernel methods. And both of them involve a quadratic. So one is you say there's some quadratic function, which we're going to write as u1 k inverse u, which is bounded, right? So k inverse is going to be symmetric positive definite typically. Yes, you can do all this stuff for conditionally positive definite kernels. That's not today's talk. So we're going to say that that's bounded by some number, right? 1 is as convenient as any other number. And if I give you that information, that this quadratic form is bounded for the pair u1, u2, then you've got a reasonable way of talking about what u2 could be, right? So you're going to look at a cross-section of this ellipsoid, which is itself an ellipsoid, and you can write down what the center looks like. So you've got this k21, k11 inverse u1 piece. That's going to be your prediction. And you've also got some notion of what the shape of that cross-sectional ellipsoid is. It's going to be another quadratic form, and the quadratic involved is going to involve S inverse. So we're going to have this optimal recovery property that W is as good a solution as you can pick if you care about worst case error. And the worst case error you can get is given in terms of S. Okay, so that's a purely deterministic type of way of thinking about things, and you say your errors are all worst case. The other way that you can think about things is to say, let's make a probabilistic assumption. So we'll be Bayesian, and we'll assume that we've got a prior on the world that u1 and u2 were jointly drawn from some Gaussian. And now we care about what's the posterior distribution for u2 conditioned on the random variable u1 being equal to u1. And the answer is you can do some calculation. And it's, again, a Gaussian random variable, right? So the nice thing about Gaussians is you do a lot of things to them and you get Gaussians out. And the mean is going to be this k21, k11 inverse u1. So the same thing that we saw as the center point for a ball previously. And the covariance matrix is going to be this Schur complement S, which is the same thing that we saw in the previous slide as the quadratic form that describes the cross-sectional ellipsoid. So either of these, as long as you're dealing with linear measurements, gives you the same types of predictions, but there's a different interpretation for the error. Fortunately, and there's a bunch of other stories that you can tell as well, right? So I see 4 of them frequently, right? So one of them is you're defining a norm ball in some reproducing kernel Hilbert space. That's equivalent to the first one that I showed you. Another one is that you've got a covariance for a Gaussian process. That's equivalent to the second one that I showed you. You can also talk about things in terms of feature maps, and we saw that a little bit yesterday, where you've got some fixed nonlinearity mapping your original domain into a high-dimensional space, and you compose that with a data-dependent linear transformation. And all of these are interesting different ways of thinking about essentially the same linear algebra at the end, right? So whether you're talking about radial basis functions or kernel ridge regression or Gaussian processes or something else, at the end of the day, in order to do predictions, you're going to be solving some linear systems. And if you care about choosing what kernel to use out of a family of possible kernels, you'll be doing, again, some linear algebra that bears a great family resemblance to other linear algebra that you might do in this domain. So I'm going to be talking in the language of Gaussian processes today, partly because that's what my collaborators on this like. But almost everything that I say can transfer to other domains where kernel methods are used. So Gaussian processes, this is a key building block for machine learning and also spatiotemporal statistics. It actually turns out that my undergrad research project way back when, slightly over 20 years ago now, involved nonlinear transformation on top of a Gaussian process. So from some perspective, I've been dealing with this for a long time. From another perspective, I got called into that because I could make linear algebra go fast. So it's the same reason that I got called in on this one. There's close connections to integral equations, and I'll touch on that briefly. There's also close connections to other types of kernel regression methods. The nice thing about this is that most of the action is in a linear piece. So most of the work that you have to do is linear algebra. Unfortunately, it's linear algebra with dense matrices. And those dense matrices are number of data points by number of data points. So if you've got a large number of data points, this starts to become unpleasant pretty quickly, right? So if you're dealing with a couple hundred or a couple thousand, maybe you're happy. As soon as you start dealing with tens of thousands or millions, you don't really want to use dense methods anymore, right? So the question is, how do we make these methods scale to very large data sets, given that you've got this dense linear algebra problem sitting in the middle, right? Okay, so Paul showed a picture of a Gaussian process yesterday. I'll show the same picture, right? So you've got a mean field, you've got standard sort of a confidence interval, or there's various ways of thinking about it, but something that tells you the pointwise variance. And then you've got a bunch of realizations which you can't see because the projector doesn't show the shade of gray that I used. But you can take my word for it that they're there behind the scenes. So that's the picture. You can think about it symbolically as being the generalization of a multivariate normal distribution, right? So some of our favorite distributions in the world, if you're dealing with scalars, it's just the regular normal distribution, right? If you're in Rn, it gets a little bit more complicated. If you're looking at functions from a d-dimensional domain, or from whatever domain really, into R, it gets a little bit more complicated. How do you deal with this now infinite dimensional thing? You deal with it a finite slice at a time. So the way that we're going to reason about GPs is we'll look at a finite set of points of interest. So these are going to be the points where you've got data and the points where you care about sampling the function, right? They can be fictional points. And we're going to say that those points are distributed. If you just look at the values at those points, the values at those points are each Gaussian random variables, and they have some mean and correlation structure. So you've got a multivariate Gaussian for the function values at those points. And just to set notation, I'm going to use the convention that capital X is a set of points, or a list of points. And if I write function with a subscript capital X, that means the vector of function values. And if I write K, which is my kernel, with 2 subscript capital X, that means the matrix that you get by evaluating at every possible pair of functions. And sometimes the X in question will be unambiguous, and I'll just write K, and it makes my notation simpler. Okay, so in order to define a Gaussian process, we need some way of getting our handle on that covariance matrix, right? That's, potentially need a mean field as well, but really 90% of the time when you see Gaussian processes, people say assume a mean field of 0, right? But the real key for a lot of this is what is this covariance matrix? So for today, I'm going to require that we always have positive definite, or at least positive semi-definite kernels. So that means that any time that you take a matrix where you sample your kernels to get the entries, that matrix is going to be positive definite. Much of the time, although not always, we assume that our kernels are also stationary and isotropic, so that they don't vary over space, and they only depend on the distances between points, right? And so if you've got something that's stationary and isotropic, you can say that the kernel is really just a function of a distance between points, or a radius, hence the name radial basis functions. Now, if I tell you here's a kernel, often I will give you not one function, but a parametric family of functions. And I say, I don't know how to pick the parameters, you choose, right? So you saw some of this yesterday. If you've got length scale parameters, or sometimes you've got discrete parameters as well, for example, in the case of Matern. And so I'm going to suppress that hyperparameter vector theta when it's not important, but it is going to be important some of the time. So if you see theta appearing and disappearing, it's because I didn't feel like writing it when I didn't need it, but I did write it when I did need it. Okay, so there's several kernels that are particularly popular. The one that is probably the most popular in machine learning is the squared exponential, which drives me nuts because, of course, squared exponential has the same form as a Gaussian. And so there are some people who have enough surface knowledge of Gaussian processes to know what it is, but not enough knowledge to realize that the Gaussian doesn't refer to the kernel, and you can do Gaussian processes with other kernels than the squared exponential. Another popular family is the Matern family, and I've got those drawn in colors that fortunately are showing up here. So the squared exponential is exactly what it sounds like. It's e to the minus r squared over 2, or over 2l, where you've got a 2l squared, where you've got a length scale, possibly multiplied by some scaling factor in front. That's very nice and smooth at the origin. These other kernels are going to be a little bit pointier at the origin. The Matern kernels are, as the index goes up, getting smoother and smoother. So Matern 1/2 is this green one that's extremely pointy at the origin. It doesn't have even derivatives. Matern 3/2 has derivative 0 at the origin, but it doesn't have second derivatives, and so on. So depending on what kernel you use, you're making implicitly different assumptions about the underlying function. So the smoother the kernel, the more you're saying, I think I've got a smooth underlying function. And so the choice of kernels makes a real difference for modeling. And one of the things that's not necessarily purely linear algebraic problem is, how do you choose the right kernel family? Well, you have to know something about the family of functions that you're interested in approximating and how smooth it's reasonable to talk about making them. And there was this comment about inductive bias yesterday, right? This is the point. You can also come up with more exotic kernels. So my collaborator, Andrew Wilson, likes to do this idea of deep kernel learning, where he puts in a deep neural network and that computes his kernel. And then he does a Gaussian process at the end. It seems to work pretty well for some things. And it certainly makes students who think that anything involving neural networks is cool very happy. So let's take the, yes?
Can I just ask you about that question? So one of the common things you always get asked, I always get asked, is what kernel should I use? Or what, in these highly flexible frameworks, what should I use?
Right.
And what do you use to answer for that question?
So how much regularity does the function have? So there's good choices. So if you believe that your function is really extremely smooth, then a squared exponential is not a bad kernel. If you think that it's analytic and maybe even nicer than analytic. If you think I've got some discontinuities in my first derivative, maybe you should use something like Matern 1/2, where the underlying reproducing kernel Hilbert space includes functions that look like that, right? So in some ways, this is one of the things that I think is easier to talk about in the deterministic framework, because there you can actually talk about what's the set of functions to which you can actually converge with these methods, right? Okay, so what's the implication though? So there's modeling implications for your choice of kernels. There's also implications for the linear algebra. So all of these kernels are going to give us positive definite kernel matrices. But they're not necessarily going to be very well-conditioned positive definite kernel matrices, right? So the squared exponential is an extreme case that the eigenvalues decay faster than exponentially. And it doesn't depend on the number of points either. It depends on your length scale and how big your domain is. But you crowd more and more points in, doesn't matter how you distribute them, the ill conditioning is going to catch up with you very quickly, right? So it does depend on the dimension, that's correct. There's a result due to Weil that talks about the eigenvalues of an associated integral kernel, but you can actually map those into bounds on the eigenvalues of your kernel matrices. It says if you've got a nu times continuously differentiable kernel, then your eigenvalues should decay like order n to the minus nu minus a half. So that tells you something about what you expect. So very rough kernels, the eigenvalues don't decay too fast. Very smooth, it decays extremely quickly. Now often what we're going to do is add a small term for regularization, so some sigma squared I, which means that any eigenvalue that's significantly smaller than this sigma squared term, that which you think of as a noise in our data, is going to be effectively wiped out. And then we're thinking about something that looks like multiple of the identity plus low rank, or at least not super high rank, and we can start to take advantage of that structure. Okay, so let's talk about that sigma squared I, right? So again, this is the Bayesian framework. You can do everything here in a deterministic framework as well. And you get what are called smoothing splines. Those of you who are interested in the connections, the book that I would actually go to for that is the one by Grace Waba, who knows both literatures pretty well. Right, so in this case, we're going to say, suppose that our data is fit to not exact function values, but function values plus a little bit of noise, right? So the measurements that we've got, or the function values that we've got, have some noise, which we assume is Gaussian, and typically we assume that it's uncorrelated, although it doesn't have to be, right? So we've got a little bit of independent Gaussian noise for every measurement. And so now if you make that assumption, the posterior for your measurements involves not the kernel matrix, but the kernel matrix plus this W term. That gives you a little bit of regularization. And so what are we going to want to do? We're going to want to pick the kernel. We're going to want to solve linear systems involving this kernel matrix plus the regularization in order to get weights. We're going to plug those in order to be able to predict the behavior of our function at various points or evaluate a mean field. And depending on what we're doing, we may want this notion of predictive variance or a power function in order to decide how confident we are if you're doing Bayesian optimization or if you're doing certain families of deterministic optimization. Again, I like the deterministic version better, but the Bayesian version seems to be more popular at this point. Right? So what's the expensive bit here? Well, you see right here and right here you've got this k tilde inverse, and k tilde is a giant dense matrix, right? Number of data points by number of data points. So how do we deal with that? Well, before I talk about how to deal with that, let's talk about this other issue, which is how do we decide which kernel to use? And there's a couple of different ways to do this as well. They boil down to the same linear algebra tricks involving traces. So if anybody wants to hear the leave one out cross-validation version of this story, I'll tell you about it afterwards. But I'm going to focus on something that you saw yesterday, which is we'll do maximum likelihood estimation in order to try and get the kernel hyperparameters, right? So we've got our data, which is essentially distributed according to a normal distribution. There's some parameters that tell us about our covariance matrix, and we're going to maximize the log likelihood, so log of the probability distribution, and that's going to give us log likelihood of the function given the data. And we get a couple of different terms, right? So we get one term that comes from the normalization constant, that doesn't depend on the hyperparameters at all. We won't worry about this, right? So this is the square root of 2 pi to the n power that occurs when you're writing down the formula for a multivariate normal. Then you've got a piece that depends on your data, right? So that's taking log of e to the minus 1/2 quadratic form, right? So the thing that pops out there is going to be this minus 1/2 y minus mu field transpose times c. That we're used to dealing with, right? So we know how to optimize quadratics and how to deal with quadratics. And then you've got this piece that involves the log of the determinant of the kernel matrix, right? So that comes about because of the normalization constant in the multivariate normal. And that part seems a little bit awkward to deal with, right? So if you've taken a numerical linear algebra class, like the one that David is teaching, you may have seen Krylov subspace methods, and you know that you can scale up the solvers for large linear systems or optimizing large quadratics, which is essentially the same thing. But what about computing log determinants for large systems? Right? Okay, so what are our scalability bottlenecks here? The first one is the solve, right? So, and if we were to do this in the most obvious way, forget about any fancy iterative methods, we would say do a factorization of k tilde, right? Cholesky or something like that. So that's order n cubed. And then we're going to do this hyperparameter maximum likelihood estimation. And for that, we're going to want to compute both the log determinant of k, and we also probably want to compute derivatives with respect to the hyperparameters if we're doing something gradient based, right? And there you get this thing that involves trace of k inverse times derivatives of k, right? So you've got log determinants and traces of matrices, both of them somewhat unpleasant to deal with if you don't know how to deal with them, right? Okay, so you've got order n cubed to do your basic regression task and also order n cubed work per step in order to do the hyperparameter optimization. And if n is at all big, this gets unpleasant, right? So if n is a couple hundred to maybe 1,000 or 2,000, this is actually okay, right? But we're interested in bigger than that. So how do we deal with things that are bigger than that? One thing that we can do is generalize the factorization methods, and there's been some really interesting work recently. I know Mihai has been doing some things too. I'm more familiar with stuff that Liesheng Ying and Anil Damle have been doing with rank structured factorizations of kernel matrices. I'll give you a flavor of how this might work in the simplest case where your kernel matrix is essentially just low rank. But I want to focus mostly today on the case where we avoid factorizations altogether and just assume that we've got the ability to do fast matrix vector multiplies by the kernel matrix, right? And the question here is really, if all you can do is fast matrix vector multiplies by the kernel matrix, we know how to solve linear systems. How do you do determinants and traces? Yes?
So just are you assuming the kernel matrix is formed in memory? So
no.
Okay.
Right. So all you have is black box. Right?
Okay.
Okay. So the simplest thing that I know how to do is, and this is stuff that actually I think is in the GPyTorch, and appears as a piece of a NIPS paper that's coming out. So what if you've got something that's really a smooth enough kernel with long enough length scale that it pretty much looks like multiple of the identity plus low rank, right? So what we're going to do is to say our kernel matrix is effectively low rank. If you've got a squared exponential kernel, it turns out that the eigenvalue decay is fast enough that you can prove that pivoted Cholesky does a pretty good job of being a rank revealing decomposition for this. Nice thing about pivoted Cholesky, and I'm happy to talk about the details later, is you don't actually have to compute the matrix to run pivoted Cholesky on it. You just need to be able to get the diagonal and the diagonal of the Schur complement. So you can do this in order n times m squared, where m is the rank that you're going for work. So you never need to do anything that's n squared. How do you then solve this system? Well, it actually turns out that often you want to go down far enough that your L matrix is still a little bit ill-conditioned. before you quit. So maybe solving this in the most straightforward way possible isn't the best thing to do. It turns out that you can reformulate the solve as being equivalent to computing a scaled residual in a regularized least squares problem. And if you solve that by QR, it gives you a little stability boost, right? Which is the type of thing that I don't think I could ever put into a paper on its own. It's the type of thing that I would give as a homework exercise to my students. But given that none of the people that I was working with actually knew that you could do this, and it does make a difference to the accuracy, I figure I would put it in. And then you've got the log determinant, and the log determinant you can compute via another trick. So you swap the order of the L and L transpose, and then you've got a piece that corresponds to all of the eigenvalues that you've discarded, right? So, and there's a similar cheap rearrangement for the derivatives. So there's very cheap things that you can do to deal with all of the tasks that you would like to solve when you've got something that looks like multiple of the identity plus low rank, right? And like I said, if you've got something that's got more complicated structure but still has low rank blocks in it, there's interesting rank structured factorizations that you can use. Okay, so what if you don't have that and all you have is matrix times vector, right, as a black box? So what are the basic things that you need? First, you need that black box, right? So I'll talk for a moment about how do you accomplish that. Then you need to be able to solve linear systems using that black box. We essentially know how to deal with that too. And then you need to do trace and diagonal computations using that black box. And that's the interesting bit that I'll spend the most time talking about in my remaining 10 minutes or so. Okay, so first question is, how do you do the kernel approximation? So one thing that you can do, which we already referred to, is a low rank approximation. People often do this via what they call inducing variables or inducing point methods. This works great if you've got something that's sufficiently smooth. If you've got something that's not too smooth, you may end up picking more points than you're really happy about. Another thing that you can do is sparse approximation. That's okay if you've got short length scales. Not necessarily so good in other cases. In both of these cases, you have to worry about losing definiteness. Or you could be more sophisticated. And here's one of these cases where it's really interesting to see how things get reinvented over time. So back in the 80s and 90s, the people in the integral equation world invented fast multipole methods. And that got ported into the kernel ridge regression literature. So Beatson worked with Leslie Greengard on some of this stuff. As far as I can tell, it mostly didn't make it into the Gaussian process literature. I've never figured out why. Also in the integral equation literature, there's this method by Jacob White called the Pre Corrected Fft Method, which is essentially a spectral method. So you're doing something where you're approximating your kernels at a distance via an FFT type of scheme, and then you've got a correction for the near field piece. And so it turns out that there's an analog of that that's been adopted in the Gaussian process literature that Andrew Wilson has worked on, called structured kernel interpolation. And it's essentially the same ideas without the correction. But Andrew didn't know about this until we chatted. The main restriction here is these methods tend to work best if you're in a low dimensional space. They don't scale very well with dimension. And one of the things that I'm excited about and would be happy to talk about to some of you later is some ideas we have for things that scale better with dimension. Right. Okay, so the idea with structured kernel interpolation, which is the main thing that we've actually been using in practice in this work, is you've got your data points, and then you've got some uniform mesh laid over a domain where your data points live. And that uniform mesh, you can write your behavior of your kernel at the data points by interpolating onto the uniform mesh and then interpolating back, right? The nice thing about this kernel matrix for the uniform mesh is that it has triplets or block triplets type of structure, and so we know how to deal with this very quickly using Fourier transform. So we know how to do fast multiplies by that. So you've got now something that's constructed by thing that you can multiply by fast or work with fast by Fourier methods, and a sparse interpolation matrix. And so you can deal with this type of system in order number of inducing points log number of inducing points time, which is pretty reasonable. Okay, so this gives you a fast matrix vector multiply with a symmetric approximation to your kernel matrix. You don't ever have to form the matrix in memory, right? So typically you would form W, but you wouldn't form KUU. So what can we do with this in order to solve our systems? Well, we could do conjugate gradients, but I'd like to dig down one level lower and say conjugate gradients, one way of thinking about it is you do a Lanczos decomposition. So you build up a Krylov subspace, you project onto that Krylov subspace, and you do all of your stuff on that Krylov subspace. The nice thing about thinking about this in terms of solve on a Krylov subspace is that we can use that thought for not just solving linear systems, but also approximating eigenvalues, approximating matrix functions, which is going to turn out to be useful. There's connections to quadrature and spectral measures as well. So this is fast, it's very elegant. There's some issues with understanding the relationship between the finite precision and the infinite precision behavior, which I'm not going to talk about today, but it does end up working out for our stuff. Right. Okay, so in addition to solving linear systems, the Lanczos iteration allows you to multiply function of a matrix times vector, or approximately multiply function of a matrix times a vector. And this is something that we're going to use. So the idea for this is that we're going to effectively project everything down onto a Krylov subspace, do our function computation on that Krylov subspace, and then map back. Right? So the Lanczos iteration gives us something that looks like orthogonal matrix times tridiagonal times orthogonal matrix transpose as a decomposition of our underlying matrix. So the way that we're going to do our function approximation is we've got a mapping just of that middle thing. So if I was to run everything out to exact completion, I get that f of k tilde is the same as q of f of t, so a tridiagonal that you get from running Lanczos times q transpose times b. And if you start with the vector b, you can simplify that a little bit more. And if you want to go to approximation, you can truncate after some number of steps. Right? So you truncate after k steps. And there's an error analysis framework for this, which I'm not going to go into, that has to do with connections to polynomial approximations. Okay, so one way of thinking about the method of conjugate gradients is it's exactly this framework where the function that you're applying to solve is z maps to 1 over z. Right? But you can do other functions this way. In particular, you can do the log this way. Right? And this is useful because you can write log of the determinant of a matrix as trace of the log of that matrix. Right? This is not a new observation to me. This is something that goes back at least to the 90s when people were thinking about some of these problems. And remember, in addition to having a log determinant that we care about, the other thing that we care about is derivatives of this log determinant with respect to kernel hyperparameters. That also has the form of trace of something. Right? Okay, so I claim that I've now told you how to deal with the stuff inside the trace. Right? So you've got a log of k. I know how to do log of a matrix times a vector using Lanczos. You've got k inverse. I know how to apply that to a vector using Lanczos, right? Using the same Lanczos decomposition, actually. So I can reuse some work here. Now the question is, how do I deal with the trace part, right? That outer part. Okay, so, and there's a trick. Again, a trick that I didn't come up with, but it's a good trick, so I'm happy to share it with you. And this is the notion of a stochastic trace estimator. So what we're going to do is write down a random vector. In the simplest case, you can think of the entries as being independent random variables, mean 0, variance 1. Right? So now what happens if I take the expected value of that vector z and plug it z transpose az for any a? Right? Well, I can write that thing down, right, in terms of the elements of the matrix, which I almost never do, but here I'll make an exception, right? So I've got the sum over all I and j of aij times the expected value of zij. But the fact that I've assumed that they're mean 0 and variance 1 means that that expected value of zij is exactly delta ij, right? So you're pulling out the sum of the aii elements over all i's here. So this gives you something whose expected value is the trace of A. If you want to go one step further, you can do diagonal estimation this way. And there's some stuff that I've been working on in a different context that uses that. But that's a story for another day. So again, this is not an idea that's new to me. There's a nice review from 7 years ago of work that was done in a long period previous to that by Avron and Toledo. I highly recommend it if you're interested in this type of stuff. Right, okay, so we've got now a way of approximately computing a trace, or at least computing a trace in expectation, that only involves matrix vector products, right? So I can say I've got some matrix A, multiply that A times a random probe vector Z, dot it with Z, you've gotten an estimate for the trace, right? And we've got a way of computing log times a vector. And we've got a way of solving a linear system with a right-hand side. Apply that in this case and we're good. Yes?
You do this just once, or do you do multiple of these in average?
You do multiple of these in average. It turns out that for the types of kernel systems that we're dealing with, you don't need so many in order to get reasonable estimates. Right, okay, so putting everything together, what are we going to do? We're going to pick a probe vector. We're going to do this repeatedly. Typically, we'll actually do it in a block so that we can take advantage of the cache architecture on our machines. But for each of our right-hand sides, we're going to run Lanczos from a normalized probe vector. We're going to use the same Lanczos decomposition both to estimate k inverse z and log k of z. And then we're going to do some dot products in order to get things which in expectation give us the log determinant and the derivatives of the log determinant that we care about. Right? So what's the cost per probe vector? It's one Lanczos iteration and one matvec per parameter with the derivative matrix. Right? Okay, so this turns out to be really effective in practice. For those of you who are linear algebra aficionados, yes, you could precondition this. That works pretty well too. For those of you who like to deal with Monte Carlo estimators, yes, you can use control variates. That works pretty well too, right? So you put all of these things together and you get some interesting pictures. So let me show you a picture of something that I worked on as an undergrad. So this is rainfall data from Adelaide, Australia from 24 weather stations, right? So that was the scale of the stuff that I was working on as an undergrad. Now, when I was an undergrad, the problem was really with the Bayesian part, not the Gaussian process part. So the scaling challenges were different, but it still makes it an interesting connection to say, what's the data that we're working with today? So 55,000 weather stations in the US, all of them collecting data. We look at it over time, so we've got a 4D space-time data set with lots and lots of data, much more than 24 measurements, right? So what are we going to do? We're going to look at total data set size of 628,000. We're going to train on 100,000 data points and test on the remainder. So that's the scale. We can flip the other way around. In fact, I thought we had flipped the other way around. It's possible that this is incorrect and we trained on, in fact, I think it is. Sorry. We trained on 528,000 data points and we held out 100,000 for test. We were using the structured kernel interpolation idea in order to do our fast matrix vector multiply with the kernel matrix. And we've got some comparisons in time and mean squared error between our method, the exact computation, and a somewhat hokey approximation to the log determinant that came up earlier. The mean squared error is actually rather better for us. For the exact, we only went up to, I guess, 12,000 data points because that was as much as we were willing to deal with on the computers that we had. And you can see you solve for 500,000 data points in about 15 minutes on a laptop. So it runs pretty fast. Right. The other thing that we have, and I'll skip very briefly through this because I'm about out of time, is a data set that shows that you can do this for things other than Gaussian processes, so you can do some transformation techniques and look at, for example, these Cox process models. We looked at some stuff with looking at where there's hickory trees in a certain forest in Michigan. And the interesting thing here is that the pictures that you get with exact fitting and with our method are pretty much the same. The pictures that you get with this other somewhat hokey approximation are not as nice. Oh gosh, okay. I would show you a teaser for something that's going to be in NIPS this year. So there's 2 NIPS papers that I'm involved in this year. One of them is the fast solver stuff with gPyTorch. The other one is putting in derivatives. You can reconstruct the Stanford bunny. Trust me, it's a really cool picture. I don't know why Acrobat is not allowing me to show it, but if you want to learn more, you can come and talk to me at the coffee breaks, of course, right? But there's also a NIPS paper last year that talks about the log determinant stuff that I spent most of my time on, and I sort of gave teasers for things in the 2 NIPS papers this year. And if you're interested in gPyTorch, it's up on GitHub. I'm sure that Jake and Jeff would be delighted to have more users for it. And with that, I'm out of time, and I'll take questions.